In this lecture, we're going to look at the algorithmic approach of recursion. By way of reminder, an algorithmic approach is just a set of steps that we're going to use to solve a problem. One algorithm that we've looked at was the binary search, which it was a divide and conquer approach where we would take our problem and break that down into a smaller equivalent problem that we could solve. And if we couldn't solve that problem, then we would break that down even farther until we could finally get down to a problem that was so simple that we could solve it. So to look more specifically at the binary search, the way that worked is we go to the middle element, and then we would see, does that middle element equal the value that we're looking for? If it does, that means we're done, we found the element. If not, and the key was less than the middle element, then we would repeat the binary search on the first half of the list. This is our divide and conquer approach where we're dividing our problem now and repeating that search on a smaller half. If it was greater than the element, then we do a binary search on the second half. So that would in return call our binary search algorithm. We would look at that now smaller list and see if the middle element there equals our element. If not, then we would compare the key to that middle element and do a binary search on the first half or the second half, depending on the outcome of this comparison here. So this idea of a method calling itself is known as a recursive approach or a recursive method. So a definition of that is a method that calls itself directly, or it could be indirectly through another method. So an example here, we just got this public void insert, and insert would end up calling the insert method within that. We'll get a greater understanding of this as we work through some examples in this lecture. So to give a more in-depth definition of recursion, it's just a programming technique that solves a problem by breaking the problem into smaller equivalent problems. Keyword here is equivalent. We're saying we can't solve this problem, but to solve it, we can solve a smaller equivalent problem until we break that down into a problem that's small enough that it's very easy to solve that. And then the solution to the smaller problem may be propagated back up to help us solve the larger problem. What's the idea behind recursion? It is a fundamental CS concept. It can be used to describe a certain type of data structures. For example, we could describe a list recursively. For a list is a single object followed by a list. So notice here in my definition of list, I'm using the word list, or it is just an empty list. And that's what we call our base case. So when we have a recursive definition, we're going to have a base case, which is our simple problem to solve. And then we have a recursive case, which is defined in terms of itself. And recursion does provide a more elegant solution to some type of problems that we need to solve. So let's look at a little bit more detail on using a recursive definition of a list. So let's consider ABC here and ask, is it a list of letters? Well, ABC is a letter A followed by the list BC. BC is the letter B followed by the list C. C is the letter C followed by an empty list, and this is the empty list. So this fits into our recursive definition of a list. Therefore, ABC is a list of letters. So coming back here, and again in reviewing some of our terminology here, the base case is a small, simple case that can easily be solved. In a recursive method, the only thing that it knows how to solve is the base case. And then the second component of a recursive method or a recursive function is the recursive case. And this is the case that breaks the problem into a smaller equivalent problem. So the general form of recursion is going to look like this. If we have reached our base case, we solve that directly. Otherwise, we're going to solve it in terms of a slightly easier case. So what are the characteristics now of recursion? One, we have to have a base case. Two, there is a recursive case. In other words, we can define the problem in terms of itself. Three, the recursion reduces the size of the problem. If we're breaking this problem down, on a recursive case has to make the problem smaller. And four, the recursion has to lead to the base case. If it never leads to the base case and something keeps calling itself, it's going to go into an infinite loop. So let's look at some examples here and compare the factorial as an iterative algorithm. A reminder, factorial definition, for example, 5 factorial is 5 times 4 times 3 times 2 times 1. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So if I am writing an iterative version of this, you can imagine that we're going to use a for loop. And here we're saying if n is less than 0, return 0. Otherwise, we're setting our product equal to 1. And now we're going to loop through from 1 to whatever value is passed in and keep multiplying that to perform our factorial product here. And then we're going to return that particular product. So this is something that is done iteratively. Now we can do the same thing done recursively. So defining factorial recursively is the idea of 5 factorial. Well, what does that equal? That equals 5 times 4 factorial. Notice here that we're taking our problem and we're defining it in terms of itself. So 5 factorial equals 5 times 4 factorial. Then we can say, well, what does 4 factorial equal? 4 factorial equals 4 times 3 factorial. So we're taking a problem that's slightly more difficult and saying, I can't solve this one, but let's solve something that may be a little bit easier. Or, another way to say it is a smaller problem. And then this is going to continue down until we reach the base case, which is our simple solution here that we can solve. So the base case here is going to be both 0 factorial or 1 factorial equals 1. So if we keep breaking this problem down, when we reach 1 factorial, it's going to return 1, which can then allow us to solve the rest of these problems back up. So here I can write the factorial algorithm recursively. So here I have my method declaration. I'm going to do a check for my base case and saying, have I reached my base case? If I have, then I'm going to return 1. Otherwise, what am I going to return? I'm going to return the value passed in times factorial of 1 less than that. This is my recursive case. So if I call this with the value 3, it says, well, does 3 equal 0 or 1? No. So then I say return 3 times factorial of 2. So then this comes up, calls factorial 2. Have I reached my base case? Nope. So then I'm going to return 2 times factorial of 1. So this comes up here now. It says, oh, n equals 1, so it returns 1. It returns back to the method that called it, which was the factorial 2. So this takes 2 times what was returned 1. So this returns 2. This returns back to the method that called it, which was a factorial 3. So this says now take 3 times the result of factorial 2, which is 2. 3 times 2 equals 6. It returns that. So the method calls can be written out like this. Now this is a little bit more in-depth example here. I got 5 factorial equals 5 times 4 factorial. I can't solve that till I know what the answer of 4 factorial is. 4 factorial equals 4 times 3 factorial. 3 factorial equals 3 times 2. 2 factorial equals 2 times 1 factorial. 1 factorial. I finally know that. That returns 1. So now I can say 2 times 1 returns 2. 3 times 2 returns 6. 4 times, what's the answer? 3 factorial equals 6. 4 times 6 returns 24. 4 factorial return 24. 5 times 24 equals 120. So that's an example of computing factorial both iteratively and recursively. Please note that anything that can be done recursively can be done iteratively and vice versa. It's just sometimes the solution may be more elegant using one of the approaches over the other one. Let's look at another example here of a recursive formula. Here we're saying g sub n equals g of n minus 1 plus 3 times n plus 1. Notice here g is defined in terms of itself. So this is a recursive formula, and this means we must have a base case. Here the base case is g0 equals 2. So to calculate this, what is the value of g2? Well, g2 equals what was passed in, 2. So 2 minus 1, g1 plus 3 times what was passed in, and it's 2. 3 times 2 plus 1. Now to solve this, I have to know the value of g1. g1 equals G0 plus 3 times what is n? N here is 1, plus 1 equals, well, we can't solve that till we know the value of G0. G0 now equals 2. Once I know that, then I can begin solving this. G0 equals 2. 2 plus 3 plus 1 equals 6. Now I know the value of G1, so I can solve this. G1 equals 6 plus 6 plus 1 equals 13. So that's how we solve a recursive formula. We can extend this out, and we'll see here what is the value of G4. Again, G4 is defined in terms of G3. We can't solve that till we know the value of G3. G3 equals, also in terms, defined in terms of G2, and the rest of the formula. We come all the way down to the base case. Once we do that, we can go back up to solve each of the other cases. To implement this formula recursively, what we're going to do, we have our declaration of our method here where we're passing in the value n. We're checking for our base case, because if we've reached our base case, then we're going to return here. Well, in this case, we've reached G0, we have to return 2, so return 2. Otherwise, we're going to return val. What is val equals? G sub n minus 1 plus 3 times n plus 1. So when we come down here, this is our recursive case, and we have to be able to solve the smaller case. So this method is going to end up calling itself. So this is the implementation of this recursive mathematical formula in code. Now I want to talk a little bit about the visualization of recursion and how it works with the stack. The stack is a part of memory. Last week we talked a little bit, I may have mentioned in passing, the word stack and the word heap. Remember, all our objects are allocated on the heap. The stack is used to keep up with the methods and their local variables or parameters that are part of the method as the program executes. The stack operates like a stack of trays, and there's two operations that we can do on the stack. We can put something on top of the stack, which is pushing it, and then we can take something off the top of the stack, which is called popping it. And when we work with the stack, the only place we can work off is the top of the stack. We can only push things on the top of the stack or pop things off the top of the stack. So I've got an example of a stack operation here. We start off with an empty stack. If I say push A, it puts A on the top of the stack. Push C puts C on top of the stack. And then I say pop. What that does is it's going to return me whatever's on the top of the stack, which is C. That leaves now A as the top of the stack, and then I say pop, that's going to return me whatever's on top of the stack. In this instance, it is A. So let's see how this works with the execution of our program. When you run that program, the computer creates a stack for you, and each time you invoke a method, the method, its local variables, are pushed on top of the stack. And when that method returns or exits, that method is popped off the top of the stack. So here's an example program. We have our class method calls. We have our main method, and here the main method ends up creating a new method calls object. It calls the method A, and method A ends up calling method B. So here what we're going to look at is the actual order of execution of each line of code in this method calls. So when the program starts, I come into the main method. So the first line that is executed is this line here, where it creates my new method calls object. After executing that line, it comes down here, executes this line, which then invokes method A. So we come down here to method A, where we're passing in the value 5, and here we execute this line third. In executing this line, it ends up calling method B and passing in 2 times whatever value is passed in, which then in return executes this line here in method B. When that line is done executing, it returns that. It returns here, does this calculation, and executes this line next. When that's done, it returns back and executes this line right here. So that is the order of execution. Now if we look at how this works on the call stack. On this next slide, I have a visualization of the stack. You may want to have the other slide up to watch the order of execution. So we start off with an empty stack. When we call the main method, and begin executing, it pushes our local variables on the stack, which are args, which are command line arguments, that array, and the MC, which is that local variable of the method calls object. Pushes those on the stack. As it executes, it ends up calling method A. So method A is called. When method A is called, it pushes its local variables on the stack, which are val. The value that was passed into it when it was called was the val 5, so that's assigned 5. And then it pushes n. When it's initially called, n doesn't have a value because that's assigned as that method executes. On execution of that method, it ends up calling method B. Method B, when it gets called, it pushes on its local variables here. Val gets pushed on. Val gets assigned the value 10. After that method returns, that method's going to return the value 40. So when it returns, it pops method B off the stack, and with it returns the value 40 and returns that to method A and uses that value in that calculation of 3 times method B. Method A then finishes executing. When it finishes executing, it pops off its local variables off the top of the stack, and we return back to the main method where we're going to run that print line. When the main method is done executing, it pops off everything, all its local variables off the stack, and our stack then is empty at the end of our program execution. So now when we look at this with the recursive method, it works the same way, except when it's called, it's calling itself, so it just pushes itself on top of the stack again. But remember, on each invocation of the method, it's going to have its own local variable value. So by way of reminder, here's our recursive implementation of that recursive formula gn. Now if we look at the execution of G2, when G2 is called, it comes in here and it pushes on there its local variables, which are going to be the n and the val. When it's initially called, n has the value 2. It goes through there, it reaches the line where it says val equals g of 2 minus 1, g1. So now g1 is called. When g1 is called, it pushes n and val on the stack. These are its own local variables for the invocation of g1. Notice here that n equals 1. Well, in solving that, it has to end up calling g0. So when g0 is called, n equals 0. We don't know the value of 0. At this point, it returns 2. So when g0 is done executing, it returns the value 2. And so when it returns value 2, 2 gets assigned a val. So then g1 can finish executing. It then returns, and when it returns, it pops its local variables off the stack. And now we're back to the invocation of g2. G2 can then say return val, which now has the value 6 because that's what was returned when g1 was called. And it can do the calculation, and it then returns 13 to whomever called g2. So with recursive methods, again, each invocation, it pushes its own local variables on the stack. Now, as I said earlier, anything that's done recursively can be done iteratively. So here's another example of taking that gn and doing that iteratively. Now note, sometimes the implementation of doing something iteratively may be a lot more difficult than doing it recursively, or vice versa. But again, anything done iteratively can always be done recursively. So let's compare recursion versus iteration. Iteration uses repetitive structures, for example, like for, while, or do while loops to iterate through whatever it's doing. The repetition is through explicit use of these type of structures, and it terminates when our loop condition fails, when we've done everything that we need to do as we're iterating through. And the repetition is usually controlled by using a counter, and this is what we call a bottom-up approach. Whereas the recursion, we use selection structures like if and if-else, or switch statements. Our repetition occurs through repeated method calls to the same method. The method terminates when our base case is finally satisfied through reducing the size of our problem until we reach our base case. And we control our repetition by dividing the problem into a simpler one. And this is known as a divide and conquer approach. So that's all I'm going to talk about on recursion. If you need some more detail, the book does a good job of explaining this also.